Hey there, tech enthusiasts! Welcome back, where we break down complex concepts into bite-sized pieces you can easily digest. Today, we're diving into a fundamental concept in the world of artificial intelligence and machine learning, the activation function. Whether you're a seasoned developer or just starting your journey in AI, understanding activation functions is key to grasping how neural networks operate. So, let's get started! But first, have you ever wondered how a neural network decides when to activate a neuron? What role does an activation function play in this decision-making process? Well, stick around, because that's exactly what we're going to explore. To understand activation functions, we first need to grasp what a neural network is. Simply put, a neural network is a series of algorithms that attempts to recognize underlying relationships in a set of data. It's inspired by the way the human brain works, consisting of interconnected nodes, or neurons, that process information. Now, when we talk about these neurons, we need to discuss how they determine whether to activate or not. This is where the activation function comes into play. An activation function is a mathematical equation that determines the output of a neural network node given an input or set of inputs. It essentially decides whether a neuron should be activated based on the weighted sum of its inputs. Let's break this down a bit further. Imagine a neuron receiving multiple inputs. These could be features of an image, words in a sentence, or any data point relevant to the task at hand. Each of these inputs is multiplied by a weight, which signifies its importance. The neuron sums these weighted inputs, adds a bias, and then passes this value through the activation function. Now, there are several types of activation functions, each with its own unique characteristics and applications. Let's explore a few of the most common ones. First, the step function. This is the simplest activation function. It outputs either a 0 or a 1, depending on whether the input exceeds a certain threshold. While intuitive, it's not commonly used in practice because it can lead to issues with gradient descent during training. Next, the sigmoid function. This function outputs values between 0 and 1, which makes it useful for binary classification tasks. However, it has a major drawback known as the vanishing gradient problem, where gradients become very small, making it hard for the network to learn. Then we have tan, or hyperbolic tangent. This function is similar to the sigmoid but outputs values between -1 and 1. Though it mitigates the vanishing gradient issue somewhat, it can still suffer from similar problems. One of the most popular is ReLU, the rectified linear unit. It outputs the input directly if it's positive, otherwise, it outputs 0. ReLU is computationally efficient and helps combat the vanishing gradient problem, but it can lead to dying ReLU where neurons can sometimes get stuck during training. Finally, leaky ReLU. This is a variation of ReLU that allows a small, non-zero, constant gradient when the unit is inactive, which helps to keep the gradient flow alive. These activation functions play a critical role in the learning process of neural networks. They introduce nonlinearity into the model, allowing it to learn from the complex patterns within data. Without activation functions, a neural network would just be a linear regression model, meaning it could only learn linear relationships. When designing neural networks, choosing the right activation function can significantly impact performance. For instance, if you're working on a binary classification problem, you might opt for a sigmoid function. In contrast, for a multi-class classification problem, you might use softmax in the output layer, which normalizes the outputs to represent probabilities. In summary, activation functions are vital components of neural networks that determine whether a neuron should activate based on input data. From the simple step function to the more complex ReLU and its variants, these functions help neural networks learn intricate patterns and make accurate predictions. So, the next time you are working on a neural network project, take a moment to evaluate which activation function best suits your needs. Remember, the choice of activation function can be the difference between a successful model and one that struggles to learn. If you found this video helpful, don't forget to give it a thumbs up, subscribe for more educational content, and hit that notification bell to stay updated on our latest uploads. Have any questions or comments? Drop them below, we love hearing from you. Thanks for watching, and we'll see you next time.